this series in the Latinx Chem 2021 event on Twitter. Yesterday we had these poster presentations, and today we have earlier we had a presentation from Professor Liliana Quintanar, and now is the turn of Professor Diego Solís Ibarra. I'm gonna allow to introduce him a little bit. So Diego graduated with honors with a bachelor degree in chemistry in 2008 from the School of Chemistry at UNAM. Later, in 2012, he received a PhD degree in chemical sciences from his alma mater, also UNAM, under the supervision of Professor Wojtek Jancic. Later, he did a postdoctoral stay at Stanford University with Hamemala Karunadasa, working with inorganic compounds. Now, his lines of research are focused on the perovskite solar cells, hybrid materials, and their applications in photovoltaics, for example, LEDs or solar cells, lead-free perovskites for application in solar cells, and also fluorescent nanoparticles and photocatalysis. But most importantly, this year, Diego was selected as part of CNN News Talented 12, which is a distinction that is given to young scientists whose research work is considered to change the global perception and will have a global impact within the following years. So it's really a pleasure to have you here. And more importantly, I consider him a friend. He's a very nice mentor, supervisor, and very smart guy to work with. Thank you very much, Diego, for giving us this presentation. Go ahead.
Thanks a lot, Braulio, and thanks a lot to the organizing committee for giving me the opportunity to share some of the science that we do. So in a little bit, I'm going to tell you a little bit about perovskites. But before doing that, I would like to tell you a little bit of my story and tell you why I believe Latinx Chem is such an important project and such an important event. As Braulio briefly mentioned, my academic journey started at UNAM and finished at UNAM. I did my bachelor's, my PhD, and now I'm a professor at UNAM here at the Instituto de Materiales. But also during my academic journey, I was fortunate enough to go to different places around the world and to further my education. And when going abroad, I often receive questions or comments regarding the science in Mexico. For example, I would get questions such as, can you do science in Mexico? Can you get a PhD in Mexico? Do you have instruments to do science? And at first it took me by surprise, those comments. I didn't know what to make of them, and later on I took them personal and a little bit annoying. So I made that one of my personal goals, to show that Latin Americans and people doing science in Latin America can do a great job, can do great science, and can really contribute to the entire community, to the entire world. And this is where Latinx Chem plays such an important role, because Latinx Chem fights that bias or fights that lack of information about Latin American science and Latin American chemistry by showcasing all of the amazing science that Latin American scientists or people in Latin America are doing. And I think that is tremendously powerful. And for that, I congratulate the organizing committee. I congratulate all of you that are here listening to me and to the other seminar. And I congratulate everyone that has put a poster. We've seen a lot of really great science going on. And this is a great showcase of the science that we can do. And I really think that this is a really important step and a really big contribution to show the Latin American chemistry. So congratulations to everyone, and thank you for being here. I think it's really a great event, and I'm sure it will continue to grow and continue to help disseminate this message. Okay, so having said that, as I said, I'm going to tell you a little bit about perovskite solar cells and perovskites in general. And by now, many of you have probably already heard in the news, in the videos, or in social media, something about perovskite solar cells. There's been quite a few articles or posts. And more recently, there has even been some like more traditional news outlets such as NBC make some noise about perovskite solar cells. You might have even heard or seen a graph such as this, in which they show that perovskite solar cells have gone from less than 4% to well over 25% in less than a decade. And also that this is extremely fast as compared to other technologies such as crystalline silicon. So there's definitely a lot of excitement in the community, and there's a lot of potential application, not only on solar cells, but there's a lot of potential in these materials. But I want to tell you first what's a perovskite and things that are not as discussed as I think they should be. So first, I would like to get everyone in the same page and talk about what is a perovskite. So there are two uses of the word perovskite. The first is when we're referring to the mineral calcium titanate. Calcium titanate was first discovered in the 19th century by Gustav Rose. And it's this mineral with this particular formula and this very particular structure, which is formed by these octahedra that are sharing their vertices and forming this three-dimensional structure where there's these cavities that host another cation here. In this case, calcium. Since this was the first structure like this one reported or shown, from then on, like every material that has a structure that is similar to calcium titanate, we call a perovskite. And these days, the term perovskite has been used quite liberally, and many things are called perovskites. So that might be a topic of discussion for another day, but remember that it's just similar. It doesn't have to be exactly the same, although most perovskites, and by the most traditional definition, it should also have this sort of formula. As I showed you before, like it's not only calcium titanate, but you can think about replacing all of the atoms in that formula. Here, for example, when I replace oxygen by nitrogen or sulfur, the charges changes, and now I have completely different elements in the other positions. So by changing the elements, you can incorporate pretty much any element in the periodic table in a perovskite type structure. And with that, changing that composition results all kind of different properties and all kind of different applications. Just to give you a clue, perovskites can have such a wide range of properties or applications as conductors, semiconductors, insulators, and even semiconductors, of course, depending on the specific composition or a specific formula of that particular perovskite. They can have ferroelectric, piezoelectric, thermoelectric. They can be used as ionic conductors, membranes, quantum materials, and a long list of etc. So they can be used in several different things. One particular family of perovskites is what we call the halide perovskites. Halide perovskites are these where we substitute X, the X position, with an halide, such as chloride, bromide, or iodide. And in particular, this family with lead perovskite has shown to have really interesting properties in the photovoltaic world, as we'll see in a little bit. And another variant of that is when we replace these traditional inorganic cations, such as cesium, for an organic adherent such as methylammonium. So now we have what we call a hybrid perovskite because it comes from meshing the organic and inorganic parts into a single material. So this is a quick introduction to perovskites. And this particular hybrid perovskite, methylammonium lead iodide, that I show here, or similar materials, are the ones that are mostly used for solar cells. And they have a lot of great properties that you might have heard of. For example, they can be made out of cheap precursors. They have high conversion efficiency, as I already showed you. They have high absorption coefficients, which allows you to build really thin and light solar cells. They have PLQEs, which is the photoluminescent quantum yield near unity, which is really good and could be helpful for not only solar cells, but other applications. They have benign defects, which is also really important because it helps you build them from cheap materials. They have good electromagnetic transport properties. Their properties can be tuned, and they have very low exciton binding energy. So these are all great properties. But what most people won't discuss or are not really telling you enough is that they also have some cons. Okay, so first of course is the concern about lead toxicity. As you probably know, lead is a toxic element. And there's some concern that deploying lots of perovskite solar cells might end up leaving some lead in wastewater or eventually in food. I mean, it's certainly a concern. Then there's some issues with moisture and light instability, which is certainly not ideal. There's still some issues with scalability. So in short, we can do great cells when they're really small, but if we can do it in bigger areas or in bigger scales, it becomes really challenging to maintain that efficiency that I told you about. And then last, we don't know much about the lifetime of these materials. How much will they last? Having been around only for a decade mostly, to know how will they respond in a working environment for over 10 years, which is what you ideally would like them to last. Okay, so here is a list, and of course, we look at this and we, in our group, we try to do two things. To take these pros or these amazing properties and try to use it for different applications or different problems. Or the other one is trying to help address some of the cons of these materials. And we do so by a synthetic approach. We're a synthetic group in our core. So we try to develop new materials for these kind of problems. So to give you an idea, here's a few projects that we have in our group. We work with some luminescent nanoparticles, lead-free perovskites, hybrid to the perovskites. We try to do some wide LEDs, Cara materials. We do some passivation schemes, and so on and so forth. But today I would like to tell you a little bit about the story about how can we address some of the toxicity and stability issues of the perovskite, and this is how we develop new materials trying to address this. Okay, before I start, this is a work led by these three students, Dr. Brenda Vargas, Maestro Raul Torres, and chemist Diana Castillo. They were the ones that developed most of this work. Of course, we had some wonderful collaboration, but these were the main students working in this, so I wanted to acknowledge their work. And as I said, the motivation was mostly to address the lead toxicity of the materials and see if we can find a suitable replacement of lead in these materials. So what are the alternatives to lead? The first chemical thought would be to go just above or below the periodic table to elements, in this case like germanium or tin. But unfortunately, those are even more sensitive to oxygen. So although they work at some degree, it might be even harder. It's definitely harder to work with these than with lead. So there might not be the idea of replacing to lead. Then you could think of many other 2+ elements that are in the periodic table. But you can also quickly start to eliminate some of them. For example, you can think about of these for being even like way toxic, way more toxic than lead, or these ones for being way more expensive. And there's a lot of reason why all these others don't work. Copper, it might be an exception, could be really interesting because it's abundant, it's not toxic, and people have indeed tried this. However, the results are not really promising, and the efficiency in solar cells have been lacking like quite a bit. So this was the original report, which reported like a 0.02% efficiency, which is not very good. And there's have been some improvement, but they're still not past the 1% mark. So this doesn't seem like a really promising alternative, and we can discuss why in maybe another time. So what it started like, there's a lot of options, ended up with not that many options. So in come the term double-perovskite. And double-perovskites are actually really simple to understand. If you get this complicated math formula, which says 2 + 2, it's equals to 1 + 3. And I think you can get double-perovskites because, so what we do is we replace two metal 2 cations with one, which has a +1 charge, and another one has a +3 charge. And in this way, we can replace metals that only have this stable oxidation state for another set of metals. And now we can also do permutation of those metals. So how does it look? This is an example. This is not our work, but this is how it can be seen, right? So in here you're replacing a 2+ metal for silver and bismuth, and create an alternative perovskite lattice which has one octaedra of each other. And so this can have really interesting implications. So now you can think about the double-perovskite chemical space. Now you can add metals that are only stable in the 1+ and the 3+ oxidation state. And you can also do permutations. So that gives you quite a lot more possibilities. So here we started to work. This was around 2016 or so. And so I asked my student Brenda to start looking for alternatives of what elements could we work on. So we settled on copper and antimony for several reasons. First, they're both abundant and relatively non-toxic. Copper and antimony have shown to be good absorbers for other PV devices. And there's also an abundance of copper and antimony perovskite, which suggested that we could potentially form a material like this. So Brenda went into the lab and started to try these elements, and she couldn't get anything going. She would only get separate phases or the same materials, and so on and so forth. Until one day the copper one accidentally oxidized to copper 2, and then formed this beautiful polycrystalline black powder that she was later able to crystallize. Of course, this really caught our attention because if you want to do a solar cell, you want a material that absorbs a lot of light. And black is an indication that it's absorbing a lot of light, most of the visible spectrum for sure. So we were puzzled by these results and wanted to know what was going on with this. And after running single crystal X-ray diffraction, we realized that what we got in our hands was what we later called a layered double-perovskite. And layer because it forms these inorganic layers separated by this space, and double because it has two different metals. Okay, so this was the first report of a layered double-perovskite to the best of our knowledge, and we were really excited for this. I'm not gonna give the detail of why this was the first case, but it was some sort of serendipity that is a particular family of perovskites in which as you grow the thickness of the layer, you need fractional oxidation states, or as we later find out, you would need a combination of metals to access the thicker layers, which are usually more interesting for photovoltaic applications. So here's another way of looking at them in some sort of ways, like introducing vacancy and replacing them with different elements. And what this generates is this layer perovskites. And you generate layers by changing the charge on the metal. So this is something that is done in situ. You don't have to do much work. You pretty much just put the reagents there and you get your layer material. And what was really surprising is that the prime material, the one which has only antimony, has a really large bandgap of about 3 electron volts. But what we found is that our material, once we incorporated copper, it has a much smaller bandgap of about 1 electron volt. So this is a really drastic difference between these two materials. And of course, when you're talking about 1 electron volt, you around the region where making solar cells become something interesting and something definitely possible. We also show that the stability of this material was really great. It has a great thermal stability. If you want a material for solar cells, you want it to be stable to high temperatures because it's going to be heating while exposing to sun. And as compared to other perovskites, as I mentioned, so we expose our material to relatively high humidities, and we also combine humidity plus illumination, like 4 days of simulated sun or UV and humidity, and the material stay put in all of these conditions. We see no sign of degradation, which we think it's a really great sign of stability, and it's a really great step towards that stability that we're looking for in these materials. Unfortunately, not everything is roses, and as Uncle Ben said, with great stability comes great trouble. And that's what we have found with this material. The stability comes at the cost of a really diminished usability. So far it's been really challenging to make good films, to process the materials in a way that we can actually make decent solar cells. So this is definitely a challenge, and it's something that we are currently working on to solving that. But beyond just a particular application of that material, what we think these particular materials show is that there's a lot of new possible materials that we haven't really explored, that we haven't yet known. So I'm here presenting you what we call the double layer perovskite chemical space. So now, as I told you before, now we can start doing combinations, but now remember that now they're combining metals in a 2 and 3 plus oxidation state. So again, there's a lot of elements that are stable and that could potentially be of interest for these oxidation states. So I'm highlighting a few here. And the question then was, can we actually form materials with other elements, or is that the only member of the family that we just discovered? So Brenda was quickly to prove that you could also put manganese instead of copper, and when incorporating manganese, you also change the properties of these materials. Also, very importantly, you can modulate the amount of manganese. You can do solid solutions and progressively introduce different amounts of manganese on these materials. And what this results is a modulation of the bandgap of these materials and the properties of these materials. So you can see here that the manganese-only material has this pale pink color, the color traditional of manganese. And as you go to the copper-only material, you get the bandgap of 1 electron volt, and depending on the concentration, you get this plethora of different properties or different bandgaps. Of course, when you're talking about manganese and copper, you are also changing the magnetic behavior of this material, which is something that it's really interesting to explore. And what we did then was we wanted to understand these materials and understand their electronic structure. So we rely on DFT calculations, and we validate those calculations with extensive studies with XPS, X-ray absorption, and X-ray emission, which told us that we really had done a good job modeling these materials and that we really understand how to model these materials. And what this allowed us is to propose, once we understand this, to propose how we could possibly explore this space. So here's again this map. I now color coded it for different possible elements that would go in this material. But of course, as you can probably imagine, playing with all these permutations is not easy, and it can be a lot of work. So we wanted to find a smarter way to explore this space. So what Raul figured out is that we could do a combination of an experimental and a computational approach to reduce our space and try to see if we can find new materials. First, we did what we call an extended Goldschmidt study, in which, by considering the radius of the different elements, we can discern which ones are more likely to be stable. So pretty much we could see that the ones in the shaded or the gray area are the ones that should be stable according to this criteria. So now we're starting to reduce our search. Then she used DFT to calculate the relative stability of the materials as compared with the possible degradation compounds. And what ended up happening after all this is that out of 90 possible materials, we end up with 8 that our calculations and our estimation suggested that are stable. So 8 is a more decent number, and it's a number that we can experimentally try. And here's the list of materials that our calculation show or suggested that are stable and we should be able to synthesize. It was nice to see that these first ones that we previously synthesized that I already talked about are indeed predicted to be stable, which was it's an important thing, that our calculations were consistent with our previous results. And then what we were able to do is to show that all these other materials that we had in synthesis before showed to be, we were able to synthesize them and to prove that we can get to them experimentally, right? There's still a few that we've not been able to do. As you can see, well, there are chromium and iron, which their 2+ oxidation still is not their favorite. So there's definitely some work to do. But regardless, like using this approach, we were able to find 5 new different materials that were previously known and that form part of these new forms of materials that I've been telling you about, the layered double-perovskite. So now you might think, and why should I care about these family of materials, right? Okay, well, I'm going to tell you a bit of a story about these 2 materials and why we think they could be useful. So these 2 materials are some of the 2 that I mentioned. They have a similar structure. They have manganese bismuth and cadmium bismuth. And when we combine them, we find that these materials can luminance very brightly. They show that they have photoluminescence of up to 80%, which is really high, and suggests that they could be used in devices such as LEDs or maybe as phosphors in LEDs or for other applications. And we did quite a bit of studies to understand these materials. We did quite a bit for the physics studies to understand these materials, and that we think that we now know how these materials behave at the electronic structure level, which I think is really important. But also we have shown that these materials are excitonic by nature, which is really exciting for a whole new different set of experiments or a new different set of applications. So what I would like to tell you here is that I hope I've convinced you that layered double perovskites hold great potential and there's plenty of chemical space yet to be explored. So here I show a diagram, and I didn't talk much about this. We have done only a tiny bit about this, where we have hybrid layered double perovskites. And here's a little review article that we wrote last year about it. But also, I hope I show you that the diversity of layered double perovskites make them attractive candidates for several applications. So I showed you already that they can be used as phosphors. But one other application that others have shown using the same materials is that they can be used for photodetectors. This is an application that has been quite successful. As I mentioned, solar cells is still a work in progress, but we're confident that we'll eventually get there. And other possible applications are in LEDs as photocatalysts and for applications in spintronics. So we're really excited about these new family of materials. And I hope I have convinced you that there's great potential and that there's a lot of chemical space that we have yet to tap and to explore. So it's not only about solar cells, but there's still way more things to be done. With that, I would like to thank first my research group. This is my research group, which has been amazing, especially during this pandemic. That has been really hard, but they have stayed put, and they're there on the Zoom meetings, which I really appreciate. All of my collaborators, staff, of course, funding from CONACYT and UNAM. And finally, here's some of my our contact details, our webpage, and our social media platforms. So with that, I thank you all. I'm looking forward to hearing some of your questions or comments. Thank you very much.
Thank you, Diego, for this presentation. I think that there is a lot to learn about these perovskites, and I hope everybody can take the opportunity to ask some questions directly to Diego. If not, I could read them as in the previous talk. So Diego, I'm gonna jump in and ask you. So you and I, we have discussed a lot about, or sometimes about the characterization using different techniques, and of course, we have discussed the use of solid state NMR to characterize these. So sometimes it's possible. So how often do you think would you use it for the systems that you have in your lab?
I'm not using it nearly enough as I should. That's for sure. There's a lot of possibilities there, and I would certainly think that we should be using it way more. Most of these materials behave really well for NMR, especially, of course, for solid state NMR. So I think there's a lot of potential there, but to be honest, we haven't really tried much on it, so I may have to rely on you to explore that.
Yeah, no, well, I was thinking because you will probably have a different insight of the material. Maybe there is perhaps less deep than X-ray diffraction, but with the solid state NMR you can capture, I don't know, perhaps some impurities within the material or something like that. So, okay, we have some questions from the audience. So, from India, somebody asks you, does every structure following the ABX3 type is considered a perovskite? Are there any exceptions?
Yeah, there are actually many exceptions. Like there are quite a few materials that have that formula, but that they don't have a perovskite structure. So having that formula does not guarantee that you have a perovskite. But there's some likelihood. Okay, so I don't have any. I don't have any material from the top of my head right now, but there's definitely quite a few that have that formula but are not a perovskite.
Good, thank you. So another question from Anna Sanabria. This is excellent conference. Thank you. I want to know if you know there are natural types of these minerals.
Yeah, certainly there are natural type of this mineral. As I said, perovskite was first a mineral, calcium titanate, and there's also the barium titanate and even some lead oxides that are found in nature. So you can find them, and there's actually some places in the world there are tons and tons of cubic tons of perovskite materials. Not exactly the ones that we have as solar cell absorbers, but there's definitely quite a few in nature.
Thank you. So Gabriel Medina wants to ask a question.
Sí. Gracias, Braulio. So Diego, thank you very much for your webinar. So it's these systems are very interesting, but from the theoretical point of view, it's a little complicated to model them. So in your experience, what is the most serious problem in modeling this system? So because you need to consider many factors, no?
Yeah, let me go back a little bit. So if you consider, for example, these materials, which were the first that we tried to model, there are some challenges. So the first is that manganese and copper have magnetic properties. So before doing that, you have to figure out what is the best way to model the magnetic behavior. Are they paramagnetic, antiferromagnetic, ferromagnetic? And unfortunately, pretty much the only way to try that is just to run calculations, see how it behaves and what is the lowest energy. Of course, we have some clue from experiments, but even within, for example, the ferromagnetic properties, there is at least 3 different ferromagnetic properties that you have to, or arrangements that you have to consider. And for doing that, you have to construct a supercell of a few unit cells, which of course increases the calculation cost. So that's the first challenge. And then that only becomes more complicated when you combine these two metals, because now it's harder to understand the magnetic behavior, and I guess the structure possibilities increase, and therefore the magnetic possibilities increase even more. So now you have to try quite a few different electronic and magnetic structures. So that's a lot of calculations that have to be done, and to do that you have to grow a relatively big supercell. Well, maybe not that big, but maybe something around 4 unit cells, or maybe 6, depending on what you're trying to do. And that definitely makes calculations harder, slower. So that's a first challenge. And then the next challenge is, here I have elements that are relatively light, but as we move on, we definitely would like to go to heavier elements such as bismuth, and definitely putting lanthanides in there would be something interesting. But right now it's really hard to calculate such elements because we just don't have enough calculation or computing capacity. So to summarize, I think those are the main challenges.
Okay, gracias, Diego.
Okay, I have another question from the YouTube audience. Professor Victor asks if you have tried to determine the quantum yield, the emission and quantum yield of these compounds in the solid state at different, of course, solid state, at different temperatures.
Different temperatures, no. Measuring PLQs at different temperatures is not something that we're able to do. But if there's someone in the audience that can help us with that, we would love to. We've only been able to do that in solid state and at room temperature. In that scenario, the height is around 80%. We would expect that increasing the temperature would increase that yield, but no, we've not been able to try that. That would be amazing though.
But that is because you have the technique limitations, or
yeah, we just don't have the technical capabilities, and as far as I know, it's not common to do that because you either you have a cryostat or you have an integrated sphere to do those measurements. And those two are hard to combine. I mean, I know that there's some people that can do it, but it's not trivial.
excellent. So I have another question from you from the audience in this in Zoom. Are all your structures solvent free? If not, is there any dependence on solvent content or solvent nature on the properties of these materials?
Yes, all of the structures that I told you about are solvent free, and actually most of the structures that we work on are solvent free. Usually you would want that because unless there's some really non-volatile solvent, having some solvent, as you said, could affect the properties, the structure, or even completely degrade your material when heating, right? So if you want to have a material that it's going to be exposed to sunlight for years, eventually, if you have a solvent, it would most likely degrade. So ideally, you don't want to have solvents in there. So far, they don't have solvents.
Okay, thank you. But there is a trend. I correct me if I'm wrong. There is a trend to introduce different types of organic counter ions, right? So to increase or regulate the optical properties of these compounds. And so what is I'm thinking about you mentioned methyl ammonium ions, but there must be something some others that are larger than those, or not? It's not possible.
We're retaining the same 3D structures. There's a handful of those. You can do from amidinium. You can, in some cases, do ethyl ammonium. There's some cases of diethyl ammonium. Vanadium, it's another case. But it's hard to really think about going to things that are larger than that, particular for the 3D perovskites. Once you go to the 2D versions, there's certainly a lot more cations that you can incorporate, and there's something that we have been explored. I didn't talk about that, but there's definitely a lot of room to work on that.
But that is because you have problems for me, like you have segregation processes going on.
Yeah, so what happens pretty much is, let me go back a little bit. So if you consider the traditional perovskite structure, so in order to keep this inorganic frame that is shown by the blue octahedra, your cation must fit in this cavity that is defined by this cube formed by 4 octahedra. So if you change it for something that is really big, what happens is that you start, for example, layering, or even further, you can reduce the dimensionality further. So it changes the nature of the materials. We sometimes call those two-dimensional perovskites, and I have a picture. They would look something like this. This is not a great depiction, but you would have inorganic two-dimensional layers, and in the middle of the layers, you would have organic cations here. And here you can play a lot. You can put a lot of different things for sure.
Excellent. Okay, I think we don't have any more questions right now. I don't know if somebody else in the audience would like to ask a question to Diego. Well, if not, we thank you, Diego, for this such a fabulous presentation. It's quite a lot of work, and congratulations for being named Talented 12. It's very well deserved, and we are very happy for you because I don't think we haven't met another such a young talent. So congratulations, Diego, for you.
Thank you, Braulio, and thank you to the entire